transmission line, you have E field and H field, E field and H field, and so on. Okay. And this is the same picture, so I'm going to just continue. Okay. And this is a cross section of the transmission line, and this blue line are the E field lines, and then the red lines are magnetic field lines. Okay. So this is one line. This is a two-line transmission. You can see that the E field line is blue line. This is the E field line, and then the red lines are magnetic field lines. Okay. So it's a cross section of how the wave is propagation through transmission line. Okay. And again, I talked about how long the line, whether this is a transmission line or it's not a transmission line. There's no absolute definition, right? It's relative to the wavelength of the signal propagation. Basically, if this is the length of the line divided by wavelength, if this k value is greater than 1, that's one wavelength long. That's too long, right? So this key value is so-called the electrical length of the line. Okay. So when you see how long this line is, we talk about electrical length, the physical length divided by wavelength. Okay. So if this length is 1/10, less than 1/10 of wavelength, it's short enough, right? It's not that short, but it's short enough. But if it's greater than 1/10 of wavelength, then it's a transmission line. That basically means we cannot assume the voltage at these two ends of the line is the same. They're not the same. Okay. All right. So, and we have all these different transmission lines: coaxial, twin lead, microstrip, and strip lines. All these can be transmission lines. Okay. All right. I'm going to go through this very quickly. Okay. There is a part. This one is about how do you calculate the transmission line parameters. Okay. And those parameters are called per unit length capacitance and reductance of the transmission line. Okay. And I'm not going to assign any homework assignment for this. Okay, if you look at the homework assignment, it's basically about circuits instead of these kind of calculations. Usually, if I don't assign a homework assignment, I don't like to talk about this, because you're not going to review this. You're going to learn that much, right? So, but there is a way to associate transmission line circuit parameters like inductance, capacitance with field, okay, which is this capacitance calculation, field calculation of capacitance, and the field calculation of inductance. Okay, so this is a very simple example from a book by Clinton Paul. That's about transmission line, two twin lead transmission lines. Okay, so basically two lines in parallel, and then how do you calculate the inductance capacitance of this? The way to do that is a very simple approach. Okay, and the approach actually uses this starting point. Assuming you have a single line, okay, then you can calculate total flux between the cross section of this single line. Okay, let me draw a picture of this. It's a little bit hard to explain. Okay, so basically this is just one line, right, with one current. Okay, and with the current you have magnetic field. Okay, in this case magnetic field is in this direction. Okay, that's H field. Okay, so if you draw area next to the line, then you can calculate total flux, which is V. This is the flux in this area. Okay, that's not that hard, right? If you know H, then you do a surface integration, you get flux. Okay, so to do that, actually it's pretty simple. Assuming this is infinite long line, okay, then the H field by Ampere's law you have a closed line integration there. Then you can find h is equal to that. Okay, so this is h, which is equal to I over 2 pi r. Okay, that's h. Okay, then this is r. R goes from here, it goes out. That's r. Then you take 2 points along this. You call it r1 and r2. Then this length here is called z, or theta z. That's the length of the line. Then you can define an area, right? Once you define this area, you can calculate that flux, total flux in that area. That's basically the surface integration of this h over the area. Okay? And if you do that, you're going to get a total flux. Assuming that there's a material, which is u mu, then this becomes B instead of H, which is mu times H. Okay? That way you can do a surface integration to find the total flux, which will give you this expression. That's the total flux of this area. Okay? Why is it important? I'll show you why we are doing this. Okay? So that's total flux there. That's that expression. Okay? And then R is R2 over R1. All right? Now, if I need to find out the inductance between these two wires, okay? So I have one wire here, one wire here. The inductance between two wires, I have a current that goes into this wire that comes out of this wire, right? The same current, okay? That goes into this wire, comes out this wire. And this is the area of flux I'm interested, okay? Because inductance is defined as flux over current, okay? Now, if I go back to this formula, notice that I can use this expression to calculate the contribution of flux from this current and then flux from this current, right? Because this current goes into the board, it goes into the board, so the H field is in this direction. This current comes out of the board, so the H field is in this direction. Okay, so basically the total flux here is equal to phi1 plus phi2, which actually can be calculated by this. Oops, where is it now? By this expression, right? It can be calculated by this expression. Basically, if I know the length, the thickness of this wire, that's R1, and then it goes all the way into here, that's R2. For this, the total flux that's generated by this current is from R1 here to R2 at the center of this conductor, because magnetic field can go through a conductor. Okay, so basically the total flux is equal to the sum of these two flux, and then the currents are the same, so you can use this to find out the inductance. Okay, so I'm going to go through very quickly the derivation. That's the formula there. The separation is called S. In this case, from center here to center here is S, or separation. Okay, that's S. So phi1, this is expression for phi1, this is expression for phi2. This Rw2 is the radiance of the wire 2. Rw1 is the radiance of wire 1. Okay, so R stands for radiance. Okay, R stands for radiance. And then you add them together, you get total flux here. Then you take ratio of these two. Then you can express inductance this way. So the inductance between these two wires can be expressed by this expression. And there, the assumption here is there is Z is equal to 1. That will give you per unit length inductance. Basically, the length here is 1. Okay, the length here is 1. So that's how you can get per unit length inductance of these two wires. Okay, and in theory or mathematically, everything is correct. Okay, but physically, it's not correct. Okay, mathematically, everything is correct. Physically, it's not correct. Okay, why? Because if you have a current here, another current here, how do you draw flux? Magnetic flux. This is the magnetic flux here, right? This is the magnetic flux here. Further on, is this correct physics? No, it's not correct anymore. Flux cannot cross like this. That's wrong. Okay. So in practice, if you have two currents like this, okay, you're going to have something like this. Because the two flux will never cross each other, so you have a dense, very dense fluxes here, very, very coarse fluxes here. This is physics. But then if you have this situation, then you cannot apply this approach at all. Because this approach assumes, remember, to get that flux, we have to assume this is a perfect loop, right? Circle. The circle has to be perfect. You cannot have an opal here, because once you have an opal, you will not be able to do this integration. Because you cannot take H out of the equation anymore. If you have an opal, you cannot take this out. Okay, so, and this approach basically is an example to show you mathematically how we can approach to approach a problem. Okay? But physically, this approach is not really correct. Okay, and maybe what we can see is if it is correct if these two lines are very far away from each other. Okay, so that these two this flux is here and the flux is almost circular. Okay, almost a circle. But then, of course, if they're too far away from each other, then we don't care. Right? It's not a transmission line. Okay, if it's transmission line, they must be very close to each other. Okay, so this is a theoretical study. It's not really very physical. Okay, but it's okay. That's just, so you can see that how we can apply this approach to find the inductance of two wires. Okay, although in physics the physics is not correct. Okay. Similarly, we can find out the capacitance between the two wires. The same, it's almost same concept, a little bit different, but very similar. Okay, that is, we assume a single. If we have a single current, where's the eraser here? If we assume there's a single conductor, okay, let's say you have a single conductor here, and then there's a charge on this conductor, okay, and then we apply Gauss's law, then we can draw a closed surface, okay, and then Gauss's law says that if we do a closed surface integration, we're going to get, which is equal to the charge inside, right? The charge is inside, okay? And then we assume D on this surface is constant, okay? So D on this surface is constant. Then we're going to take, we can take D out of this equation. So D times 4 pi r, no, it's not 4 pi r, no. Yeah, 2 pi r. And this is 30 C here, okay? and this is R. So it's 2 pi R delta Z. That's the surface area, right? Which is equal to Q. That will give you D, which is equal to Q pi R delta Z. And that will give you E, which is equal to D times divided by epsilon. Okay. And once we know E, then we can use D to find the voltage, right, between any 2 points. So basically, if you draw a cross section of this, that's charge Q. Okay, D is in this direction, and E is also in this direction, right? E is also in this direction. This is a cross section of a current. The wire is going into the board. Okay, assuming wire is going into the board. Okay, and once we know E, given any 2 points, R1 and R2, we can find the voltage between these 2 points, right? It's just a line integration of E, R1 to R2. This will give you voltage. Okay, and that's how we can get the voltage of a single wire. Then what do we do? We have 2 wires. Now what do we do? We have 2 wires, right? This is one wire which has Q. This is another wire which has negative Q. Plus Q, negative Q. This is 2 wires, right? So how do we define capacitance between 2 wires? Capacitance is defined as Q over V. Okay? It's the same thing. We just use this theory, which will give us this capacitance. That's the capacitance expression. That's based on this discussion here. Okay, any given 2 points, we know voltage. Now what we have is the voltage between these 2 points, right? That's the voltage. Okay, and then another voltage between these 2 points. One is due to this Q, the other is due to this negative Q, but they actually add together. Okay. Because this Q and negative Q is basically double the voltage. Okay, so given this voltage due to the single wire, we put another wire there. We assume nothing else changes. Okay, and then we can just basically, and this is voltage due to Q. This is voltage due to negative Q. Then we basically add them together, right? Then you take a ratio of this Q over V. That's the calculation formula for the capacitance. Okay, and then of course you assume delta Z is 1. That will give you per unit length capacitance. Okay, again mathematically everything is correct, but physically something is wrong. What is wrong? What is wrong in terms of physics? What happens when you put 2 lines together? One has Q charge, one has negative Q charge. What doesn't happen to the flux? Okay, plus Q minus Q, right? How do you draw flux? This one's fine. This one's probably okay. This one may not be okay, right? No. Okay, if I ask you to draw flux, okay, of these 2, one is positive charge, one is negative charge. Okay. This one is a straight line, right? What about the other lines? They're not going to be straight, right? What about this line? It's going to be something like this, right? Now, what's wrong with this physics? Yeah, look at this. Look at this line. We derived all the equations based on this flux distribution, right? But then we put the two lines together. we're still applying this mathematical model to this, which is not going to be true at all. Okay? It might be true if the two lines are very, very far from each other. Maybe one is in China, the other is in America. So, but then who cares? Okay. So again, when you see mathematical formulas or conclusions, you look at the constraints. None of the mathematical solutions will apply to anything, to everything. Right? There's always constraints. Okay. You have to understand the constraints. Then you know when you can apply this, when you cannot apply. So that's why you can see here it says, if the lines are widely separated, but then if the lines are widely separated, why do you care about the interaction between the two? Okay, so that's the formula. Okay, anyway, okay. Again, there's some relationship between this capacitance and inductance. The capacitance and inductance do exist, right? Okay, how do we know there's a capacitance and inductance? Remember how we described the wave propagation? You have E field, H field, E field, H field. What is E field? Who stores the E field? The capacitance, right? Who stores the H field? The inductance. Okay, that's why we can model a transmission line can be modeled with electrical field and magnetic field interchanging to propagate through energy, or we can convert that to circuit theory. We can use capacitance and inductance, which also stores magnetic field and electrical field. Okay, so it turned out that this per unit length capacitance and multiplied by per unit length inductance is equal to mu times epsilon. Okay, and the speed of propagation is equal to 1 over square root of mu epsilon, or 1 over square root of LC. Okay, and this formula is from this textbook by Clinton Paul, but there's no derivation. So what if the lines are widely separated? You have this expression, but if they're not, you have another expression, which actually is approximation, very much approximation. Okay, all right. The transmission line model we're dealing with is a very specific transmission line. Okay, like this. This is a very nice transmission line. Okay. The wave propagated through this is called transverse electromagnetic wave. That is, the E field is in one direction, H field is in another direction. They are perpendicular from each other. Their dot product is 0. And then the energy of power density with pointing vector is in the other direction. Okay? So E cross product with H is equal to S, which is the power density. And then they are all perpendicular from each other. Okay? That's a very special electromagnetic wave, which is called transverse electromagnetic wave. Okay? And this is only one that we're talking about. And the second condition is the cross section here is electrically short.